Hi everybody, welcome to the second discussion video. I'm going to talk a little bit today about how to look at graphs, pick a graph, what the different various kinds of graphs are. So the first thing you want to do is you got to decide whether or not you're using qualitative or quantitative variables, right? So the qualitative variables, those are the ones where the values the variables can take on are one of a number of categories, right? Like a Boolean variable that can take on a value of true or false, that's a qualitative variable. Or a quantitative variable, that might be a real valued variable, some number on the number line, where you're really talking about a range of values that the variable can take on. So once you've got these ideas, first thing you're going to want to do is you can kind of organize your data into a table. You can just put the frequency, these are typically called frequency tables, but you can just put the frequency table in itself as a type of graph, typically for a qualitative variable. So the graph on the right, the lower right, below my face, this is a typical frequency table where you've got the categories are the different rows and the frequency by which these categories return. Excuse me, my throat's been bothering me for a couple of days. The frequency with which each of these categories occurs in the data, it's how many times it occurs, and then the relative frequency is like a percentage of the overall frequency that that category occurs. But you also might end up with some other situations, like you might have a real valued, like a quantitative variable that maybe you want to slice it up into a number of groups. So you might use a different type of plot, like a histogram plot. Maybe we'll talk about that a little later on. But you might end up developing a frequency table more like on the left, where you have, instead of these categories, you're basically going to create ranges for each category. And then you're going to look and see how many elements are in that range. And so that's a way of building a frequency table for a quantitative variable. And then you can see on the frequency table on the left-hand side that this is looking at a range from about 29.5 to 179.5 and cutting it up into a number of bins and then seeing how many data items fall into each bin, and then we're accumulating the total number of data items until we have all 642 data items are accounted for. So once you've got these tables, sometimes these tables are good enough if you only have a few categories to explain what's going on with your variables, but not always. And so once you've got this data, once you've got these tables, you can decide maybe I should have a graph. Maybe I should have a graph because I've got a lot of information. And what you need to do then is you need to decide what kind of graph you want. So the first kind we talked about was the frequency table, but you might also have something like a pie chart. So the pie chart is below my image again. And this is a pie chart about how many computers, how many out there, previous computer owners owned Macintoshes or Windows machines, or maybe no computers at all, before they bought a new Apple Macintosh. You can see that people who've owned Macintoshes before are highly likely to buy one. Sometimes Windows users buy one, but not often. And if someone doesn't have any computer, they're more likely even than a Windows user to buy a Macintosh. And so one of the things you have to consider, though, when you do a pie chart like this, you're making it from data shown here in this frequency table on the right, lower right. You have to decide whether or not you're going to just put the frequency or the relative frequency. I recommend, and the book recommends, relative frequency because it's hard to really get an idea of what percentage each of these pie slices are of the overall pie, right? Without actually telling the direct percentage. I mean, you can just put a number there, but then you've got to do some mental gymnastics, some math in your head to decide, how much a percentage 85 is of the total of 500. And there's no real good way to put 500 into this graph unless you're going to do it on the side, whereas everyone knows percentages of a whole only go up to 100%. So it is commonly, if you're going to use a pie chart, you definitely want to probably use percentages versus frequencies. And in general, pie charts they're not really that useful, I would think. And the book agrees that they can be kind of deceptive. They're interesting to look at, but they're not very illustrative. They don't give you good ideas about how to compare different regions together. So if you're looking at, for example, if you didn't have the percentages and you're looking at the Macintosh region versus the Windows region, you're saying, well, how many times is that Macintosh region going to be able to contain a copy of the Windows region? So you're looking at that ratio. It's really hard to see just from the surface areas in general. So it's, the pie charts, they're a little harder to understand, but people use them. People use them very often. But I think pie charts, they're most interesting when you only have a couple of big categories to look at. Maybe you have a lot of small ones, they're just going to take a sliver, but the majority of your pie is a couple of big categories. Yeah, maybe then you get an idea of how much these areas are in relation to one another. I think another big advantage of the pie chart is people often talk about in business getting a bigger slice of the pie. So it seems that in those kind of situations, it might make sense to use a pie chart so you can get people thinking in those terms if you're talking about a market size or market share of a market, for example. So for certain cases, maybe they're useful, more useful than in most cases. Another idea are bar charts. So, a bar chart, this again is, we're talking about qualitative variables here. So in these qualitative variables, you have a certain number of categories, and you're just going to represent by a solid bar. The height of that bar is going to represent how many elements are in each of those regions. And here it's a little more intuitive to compare ratios together, especially when you've got these horizontal line markers at the intervals of every 100 buyers. So then you can see quickly that, okay, maybe Macintosh is about 4 times the size of the number of Windows users, maybe a little more than 3 times the size of the number of non-users. So I do think bar charts in general are more interesting, and you can come up with sophisticated bar charts that allow you to check out and compare different regions or variables in different ways. The book has got some more illustrative examples of the different bar charts, but they're useful. Again, what you want to do is to go back. You start with your frequency table, and then you decide from the frequency table information, the information that you're organizing, what kind of chart you're going to use. And bar charts, you can really put a lot of bars on a chart, and if they're organized cleverly, and I think then they can be much more illustrative than a pie chart, simply because you're really just looking at the heights, the comparative heights, rather than the widths. So the area under the height of the bar I think has a lot more intuitive comparative power to understanding. So one of the things that people do though with these bar charts is you can really be deceptive. So one of these things is talk about lie factors, like how can we obfuscate in some way what the relative values are. An example is why don't we use an image here? We could just use an image. Let's use an image of the first iMac. The look at these different heights. So, but of course, when you scale this image up so that it is at the appropriate height, the size, the area that the image takes up also grows in width. So the whole area of the image then ends up being much larger than the area of the lesser height images because you're scaling the width, not just the height this time. And so for this region, it can be deceptive because now your intuition is maybe I should compare the surface areas of these relative images, and as you can see here, you can clearly see, okay, maybe 4 times the number of previous Windows users, previous Mac users are buying new Macs, but here it looks like a much larger number simply because the surface area of the Macintosh image is much larger than of the Windows image. So this is a way to kind of fudge the results to make them look the way you might want, actually, in some situations, if you're running a business. But and you're trying to impress people with a presentation or customers or potential business partners, like maybe you can see a use in doing that. But in science, if you're doing science, you really don't want to do that. You really want to make it, you're doing the chart to make it easy to understand, right? So we're not using these frequency tables to look at everything. You want something that at a glance conveys the information that you're trying to get across. And so, if you're trying to use these life factors to impress in some way, you're not really going to convey the information as accurately as possible, and it's something you just kind of want to avoid. Another way to fudge the information is changing the baseline. As you can see here, this bar chart, it's the same information as this bar chart, but look where we're starting our y-axis. We're not starting the y-axis as 0 as here. We're starting the y-axis at 50 or 60. Excuse me, my throat has been bothering me. So this bar chart, what this does is it actually creates a deceptive area ratio, right? So the areas now it looks like it could be 20 times as many previous Macintosh buyers are buying new Macs as Windows buyers. So it's very deceptive, and you kind of want to avoid this as well. And this often is used, I've seen this used many times if you're looking at investment presentations, etc. You're going to see stuff where it doesn't go down to 0, but in most cases, almost all cases, you're going to want to start at 0, because then the ratio of areas between the different bars are not going to accurately reflect the prevalence of the frequency that's in the frequency table. So this is another way to create a deceptive chart or deceptive graph. You don't really want to use it in science, right? Business, you got to do what you got to do, but in science, you're just trying to convey the information as clearly as possible. You're not trying to make the results hard to understand. So just go with a 0 baseline, so the ratio of areas between the bars is not distorted. Okay, so let's talk a little bit about quantitative variables. So quantitative variables, a lot of different ways to represent these variables. So again, I recommend starting with some sort of frequency chart to organize your information. And once you've got that frequency chart, you can decide how you want to display that information. In this example, so we're talking about a stem and leaf. So the way the stem and leaf goes is in this case, once again, you have a quantitative variable, but you're looking at, you might want to group these variables together. And the way they're doing it in this case is they are looking at the first digit and saying, okay, the first digit obviously is the most significant digit because it is to the highest 10th power when you're assembling a number with more than one digit. And then what they're doing is they're saying, okay, we're going to follow this now with the rest of the single digits, and each digit is to the right of the bar is a different data item. And the way you recreate that data item is you combine it with what's in front of the bar. So looking at the top image here, we're seeing that there was a 137, right? And then below that there was a 32, a 30, and then two 33s. And then below that there was a 2 28s and a 29, right? And then below that there was 2 20s, 3 21s, 3 22s, and a 23. So you can see here they didn't put all of the digits in the same line. They kind of split it up, so you've got the low end and high end digits and on different stems. You have low stems and high stems, right? So 37 is a high stem because it's above 5, and the low stems are under 32, 33, 2, 3, 3. So by counting out the number of leaves, you can get the number of elements that are in the data, right? But this is a good way to summarize the data because it saves you writing out the first digit repeatedly for all those instances. This is actually a little more flexible than you think. The bottom image here actually shows two different data sets that maybe these are a year apart. You have data for 1 year, and the next year you collect data again. And so you might have a situation where you've got 37 in 1 year, but none in the other year. So in that example, 1 year will be to the right of the stem, and the other year will be to the left of the stem, right? So the previous year is all to the left, the next year is all to the right. And it follows the same as the above graph, where you can count the number of leaves on either side to see how many data items were in each year when you collected that data set. And you can reconstruct the data set entirely by combining the stem and leaves and writing it out. But this just helps make the information a little more compact. It's also structured, right? There's an order from the lowest data elements to the top. So you do have a little bit more structure. And this will work, this will be good for a low number of, a relatively low number of data elements. You also can see a height, right? So if you're looking at the 2 stem, the low 2 stem, right, you can see that it's longer for both years. So this is almost like a bar chart turned on its side, right, where you can see by comparing the length of each of these groupings, you can see where the largest number of data elements were to fall. And so you get kind of a histogram, which we're going to talk about next. So a histogram, once again, is this situation where you have ranges, even ranges, and you're going to divide up your quantitative variable into a number of groups of ranges, and you're going to put all the data items in that range. And then you're going to see how many data items are in that range, and you're going to graph the bar for that element as high as the number of data items that are in it. And it's going to form a histogram, which is an approximation of actually the probability distribution, statistical distribution of this, of the data items, right? And one of the challenges is finding good bin sizes. You probably don't want to do too many bins. Here, I think we've done maybe 10 bins. And I think that that's a good number. Though you might need to do more or less depending on what data item you're looking at. The bins should all probably be about the same size, and it's completely fine to have empty bins. It's common, but you don't want too many empty bins. To have a couple empty bins is okay, but if you have a large number of empty bins, then you have to reduce the number of bins you're using, so you have to increase the bin size, the bin ranges, so that each bin has a chance to capture some data elements. So it's a little more informative, I would say. This is a very common graph. You're going to see it in a lot of places, and the real challenge I think here is finding good bin sizes. When constructing a graph like this, you're going to use to go back briefly, you're going to use something like this frequency table on the left here, where you have an upper limit and a lower limit. So there's your bin areas, and then you can count the number of data elements that are going to fall into that bin range, and then you can accumulate. You can create a cumulative account if you want to accumulate the bin values over time. It really depends on the kind of information that you want to show. You start with the frequency table and then decide what kind of graph you want by the information that you've collected. Another thing to notice is if you have this stem and leaf, right? So the stems, you can divide up the stems into different ranges, but in this case here, these frequencies, you can see this, the 39 goes to 49, 49 goes to 59. These bin sizes can stretch across more than one number in the front. Whereas that is a little more challenging to do here with the stem and leaf. You really can't do that. The stem has to be consistent, right? A stem doesn't range over more than one digit. But you can have more than one stem with the same digit, for sure. But in some cases, the histogram, I think, is more illustrative. But the stem and leaf is useful to bang out a small graph to show you some information if you just don't have that many bins to begin with. Okay, another idea are, and we're going to do this in a slightly reverse order, the dot plots. So the dot plots here, they show you the frequencies of a number of categories on the left-hand side, and what we're looking at is, in a retiree community playing card games. What kind of card games are being played at on each day? And you can see here that these are frequencies, and a dot represents, you look at the x-axis and you can see how many games are being played on the respective day. Black dot would be for a Sunday, a white dot would be for a Wednesday. And you can say that hearts, maybe there's 1,500 games being played of hearts on a Sunday, right? So this is really looking at the frequencies with which the games on the y-axis are occurring on these different days. And there's a number of different ways to organize these dot plots, but they are largely frequency based, and you can have more than one axis, like for example the Sunday and Wednesday axes. This is a way to combine actually two dot plots into one, just by using a different marker, a different symbol for each day in the same plot. Also a very useful graph. You also can get something called frequency polygons, and this really is similar to the dot plots. So in the dot plots, you really have these categories on the x-axis, on the y-axis, excuse me. But in the frequency polygons, the frequencies they're not really categories, although you might think, I guess you could group them as you might for a histogram. But in this case, really what you're doing is you're connecting the relative frequencies together into a line. It creates a polygon that you can compare to other polygons by superimposing multiple polygons using different colors or different symbols. You might see circles used or crosses, or as in the case of here, you might have different types of circles. So you can combine multiple frequency polygons into a single graph, and you'll see examples of that in the book. There's also an interesting option here where you can accumulate over time until all of as the accumulated frequency, as the test score goes up, you're basically looking at a particular point, you're accumulating everything you've seen to the left of the scale. And that would be the lower graph here, that you're doing that accumulation. So that could be useful. It could be useful to see how something builds up over time to account for all the data items in a data set. And finally, this one, there's a couple problems on the homework, so I really want to go over this one in a little more detail, because the box plots, you're going to see this in a lot of papers. It's very descriptive, but it's a little confusing actually to think about. The first time you see this, you might wonder, how are we going to get the information out of this? The box plot that we want to talk about is it's going to be right in the middle, right underneath the title, box plots. And this is a basic box plot here, and there are a couple of different parts to it. On the left, you will see how we are defining these different parts, right? So, and then below, you're going to see some of the labeling. So the median is going to be the horizontal bar in the middle of the box, right? That's the median score. So that's going to be, you're just going to take the middle element, you're going to sort your elements in your data, and you're just going to pick the middle one. Right, that's going to be the median. That's where you're going to put that middle horizontal bar of the box, right? And then what you're going to say is, okay, the upper hinge and the lower hinge, this is the 75th percentile and 25th percentile. So 25% of every, the lowest 25%, where that begins, you're going to put the bottom of the box, and where the top 75%, the top 25%, right, you're going to put the top bar of the box, such that everything below the top bar will be in the 75th percentile, right? And you can see that those are the first two definitions shown, the upper hinge and lower hinge on the left. So understanding these definitions really help you read the box plot. Now, the mean would be the cross in between. So that's where you sum up your values over your data set and get an average across all the data. You're going to put a little cross. And it's not necessarily going to be on the mean, but it's going to be close to it in general. But that's where the cross goes, and you can see there that they are close to the mean, but not directly on it. And sometimes you might have an outlier, so that far out value is going to be something that you're going to put just a little dot that hangs in space. So you can see that under female and the female gender above the top and bottom, and those are talked about the upper adjacent and lower adjacent. So the upper adjacent and lower adjacent, so you compute this spread, right, which is the horizontal spread is the distance between the upper hinge and lower hinge, and then you're going to create the step by multiplying that distance by 1.5, And then you get these fences, which are these regions, right, that are above and below the box plot itself, and that just shows you where to create these outside values, right? Where to mark these outside values with just a dot or something. It's like, there's a data item here, but it's not really a part of the distribution as a whole that's being represented by the box plot. It just seems to be way out there, and we don't know what happened there. Maybe it's not relevant to the box plot, to the mass, the total mass of where the data is located that's being represented by the box plot. So, but you don't want to ignore that value. That value, maybe there's something there. Maybe it was a mistake, but maybe there's something there. So you might represent it by just putting a dot that's outside the upper and lower adjacent. And you can see that in the, like I said, once again, it's going to be in the middle graph. This little dot here under the female gender, and then so the upper adjacent, lower adjacent, it's just going to be the largest value and smallest value below the upper and above the lower inner fences, right? So it's just going to be something that's going to be inside the fence or just outside it's going to be just inside the fences, right? So these fences are a region where you might want to mark these outliers, but what's the closest value to that fence, right? So I've also heard this referred to as the shadow, these upper and lower adjacent. That's the extension, right? And you can see that defined in the lower middle graph. So you can get a lot of information in these box plots. You're going to see these a lot in the literature. You want to check out and make sure that you understand what these various symbols in the box plot, what they mean. And I think that it's going to be really helpful because you can compress a lot of information into this box plot about the distribution, the mean, the median, where the 25th percentile, 75th percentile is, where the outliers are located, right? What are the smallest values that are outside of the spread, but they're not considered an outlier. That would be the upper and lower adjacent. So you can, and that just kind of gives you a range. Like we're getting the values in this range here, but they're not really outlier values because they're not in the fences, right? They're just in this, everything else is in this range. But then if you want to talk about the meat of the distribution, really we're looking at what's in between 25th and 75th percentile. So looking at the center 50%. That's really what the square, that's what the rectangle square is. You're talking about the middle 50%. And then the rest of the 25% at the bottom, 25% at the top is being represented by the shadow, or these upper and lower, in the line that connects the box to the upper and lower adjacent. The upper and lower adjacent are just the farthest values you have that aren't really outliers. And then of course your outliers are out in the fences, right? Hitting home runs. So this is a little complicated to understand. There's some homework questions that focus on the box plots. I'm pretty sure that if you're going to be asked a question on a test, it's going to be about the box plots. Make sure you know this information. Good luck on the assignment. It's due, as far as I know, it's due at midnight again tonight. And you want to make sure you do these box plots right. And I wish you guys the best of luck. Send me an email if you guys want to meet. And I'll be doing the grading for this assignment. So, early next week, I'll be looking for your questions. If you have any about how I've graded this assignment. And I will see you guys next week. Have a good weekend.